All right, in this next video, we're going to do some more multiplication rule examples, just like we did in the previous video. So first off, let's rehash some of our probability rules. The first two rules were our main ones here, that the probability of any event A has to be in between 0 and 100%. Rule number 2 was that the probability of all of our events, which make up our sample space S, must equal 100%. We talked about the complement rule, that the probability of any event not happening, and that's what that little almost to the C power represented, is equal to 1 minus the probability that the event does in fact occur. 4 was when we talked about the addition rule, that if we want to know the probability of two events happening, or in that case. Now this works for disjoint or non-disjoint events. So if A and B are disjoint, meaning that they have no overlap in a Venn diagram, that they don't happen at the same time, then this probability of A and B is 0. So then you're just adding the two separate probabilities. If they are not disjoint and there is some additional probability here, then we have to subtract that out. And then in the previous video, we talked about multiplying, or using the term and here. If we wanted to know the probability that two events happen at the same time, then we can just multiply the individual probabilities together. Now, we're going to talk more about this rule number 5 in this video. And just like we had A and B are disjoint or not disjoint, and we maybe had to subtract a value or not, we're going to talk about some scenarios of when A and B are really kind of connected together and how this might change slightly. So that's what the problem is here. The multiplication rule only works for independent events. We need a more general multiplication rule that works for all situations despite whether or not the events are independent. Now, independent versus dependent, hopefully you guys can kind of think of, scenarios of when things would be independent versus dependent. Independent just means that they have no effect on each other. They are completely independent events. If one is dependent upon the other, then there's some reliance of one event on another event. So the joint probability that both events A and B happen together can be found by using this rule here. And this looks pretty much like the same rule up here, except we've got that little addition for a conditional probability. So clear all that off real quick here. So here the probability of B, and then that line A is called the conditional probability. And anytime you see that line right there, then you can say the word given. So the probability of B given A has occurred. Okay, so you're given some extra information. We know A has occurred, so does that in fact affect the probability of event B occurring? Is it still the same, or is it now been slightly altered? Rewrite the equation above, solving for the conditional probability. So this, you don't necessarily have to do this, but if I wanted to figure out what this was, then what I could do is divide both sides by the probability of A, so that that goes away. So if I wanted to know just what is the probability of B given A, well, if I knew what the probability of A and B was, and if I knew what the probability of just A was by itself, I could divide those two probabilities, and that would give me the probability of B occurring, given A has occurred. Now, two events are independent if the knowledge that the first event occurred does not change the probability that the second occurs. If these two events are completely independent, then it doesn't matter if one event occurred or not. The probabilities stay the same. Stated mathematically, two events are independent if the probability of B given A equals the probability of B. So think about it this way. If A has no effect on B, given that you know A occurs, if A has no effect on B, then it's like it's not even really there. Like, who cares if A happened? It's just the probability that B is there. Okay? So if A has occurred or not, it really doesn't matter. It's still just like saying the probability that just B happened. Another way to think about it would be, if we took this up here And if A has no effect on it, then we can really just scratch it off. And now we're back to our multiplication rule that we discussed in the previous. All right, first example says Slim very much wants to draw 2 diamonds in a row. As he looks at his hand and at the upturned cards on the table, Slim sees 11 cards. Of these, 4 are diamonds. So draw a tree diagram for this situation complete with probabilities. All right, so he wants 2 diamonds in a row, which means he's going to get 2 cards in a row. So first card comes up, what happens? Well, one of 2 things is going to happen. Number 1, he's going to get a diamond, or he's not going to get a diamond. And notice for this, I just put diamond C, diamond complement, and the ones here represent what could happen on the first card that he sees. All right, now let's write in the probabilities here along these 2 branches of our tree diagram. Now, if he sees 11 cards, that means there are 41 cards that he is currently unaware of. Okay, and he knows that there are 4 diamonds out there out of those 11 cards. So the probability he gets a diamond going along this route of the tree diagram, well, there are 13 diamonds overall, and he's got 4 of them, so there are 9 unaccounted for. So he wants one of those 9, so it'd be 9 out of our 41 cards that are left over. And there's our 9 out of 41 probability. Now, the probability that he doesn't get a diamond, well, it's just the complement of this event. There's 32 other cards out of the 41 that aren't diamonds. So this is 32 out of 41. So there's the first card that comes along of our tree diagram. Now, if we want the second card to come along now, well, now we got to look at this in one of 2 ways. You know, if the first card was a diamond, now what could happen? Or we can look at it as, well, if the first card wasn't a diamond, now what could happen? So off each one of those ends of our branches, we're going to have 2 more branches. So let's just look at the first one right now. So notice I got 2's here to represent the second card that's coming along. So if the first card was a diamond, the second card could be another diamond, or it doesn't have to be a diamond. It could be a spade, club, or heart. Now, the probability that the second card is a diamond, well, it depends on what happened first, and we got a diamond. So instead of there being 9 diamonds, now there's only 8 diamonds left over out of 40 cards altogether. Now, we could simplify that as 1/5, but I'm just going to leave it as 8/40. Now, the probability that the second card is not a diamond, well, there were 32 cards that weren't diamonds, and after that first card, which was a diamond, I still have 32 cards that aren't diamonds. But now, instead of being out of 41, because that diamond took care of one of my 41 cards, now I have just 40 cards left over. So 32 out of 40. And notice that these 2 probabilities together need to add up to be 1. Either this is going to happen or that will happen, which makes up all of my possibilities. Same thing held true over here. 9 out of 41 and 32 out of 41 together makes 41 out of 41. So either that will happen, a diamond, or not a diamond will happen. Okay. Now, we did that for our first card being a diamond. But what if the first card wasn't a diamond? Now we have to look at that possibility. So again, I got the same 2 branches basically, but they're not necessarily going to have the same probabilities. So if the first card was not a diamond, I still have 9 diamonds out there. Out of now, though, 40 cards, because one of the 40 was the non-diamond I got on my first card. And the probability that the second card is also not a diamond, given that the first card was not a diamond. Well, if I pulled one of the 32 here, that means I have 31 leftover non-diamond cards out of 40 altogether. And again, notice 9 out of 40 and 31 out of 40 together make 100% for that particular branch. Now what we could do, and this isn't necessary, is we could look at all of the probabilities kind of as a grand finale, if you will. Okay, so if we were to go along this branch, this means we got a diamond and he got another diamond. So I can say that is first card diamond and second card diamond. Or what we could do is go along a different branch. We could say, hey, he got a diamond, but then he didn't get a diamond. So I could represent that as first card diamond and second card not diamond. Or what else could happen is the first card's not a diamond and the second card is a diamond. So first card not diamond and the second card is diamond. And then our last combination is not a diamond and not a diamond. So first card complement not diamond and second card complement not a diamond. And then we could, if we wanted to, again, this might help us out later with some questions related to this problem, we could calculate these probabilities. Okay, so first card diamond and second card diamond, well, that's nothing more than just taking the individual probabilities along those branches, the 9 out of 41, and multiplying it by the other branch along that path, the 8 out of 40. So if I take my calculator, 9 out of 41 times 8 out of 40, that gives me a little bit above 4%. Now, if I were to do the same thing and go along each of my other branches and multiply the probabilities along the way, then I would get, for this scenario, 17.56%. If I were to go along this route, I get the same answer, which seems a little weird, but if you notice my two probabilities here, really this 9 and that 9 just switch places, and this 32 and that 32 just switch places, and it doesn't matter which order that you multiply numbers in, you'll get the same answer, which is why these two answers are exactly the same. And then down for our bottom branch of getting two non-diamonds, we get a little bit over 60% chance. Now, if I wanted to double check to make sure I've done everything correctly, all four of these probabilities should add up to be 100%, and there's my total sample space. All right, so there's our tree diagram. So really again, this is the main thing that you would need for part A of this. There's our tree diagram, and there's the probabilities along each branch. If you want to go the little bit extra route and figure out all of this so that it may help you later out some future problems, you could do that. So part B says find the probability that Slim draws two diamonds in a row, which means the first card is a diamond and the second card is a diamond. Well, where did that happen at? That happened right here. And hey, we don't have to do the probability because we already did it. It's right there. So he had a little bit more than a 4% chance of getting two diamonds in a row. Now, another way we could look at this is the first card is a diamond and the second card is a diamond. We could look at that as the product of the individual probabilities, except it's not just the first card's a diamond times the second card's a diamond, because those two events are not independent. The second card as a diamond will be influenced by whether the first card was a diamond or not. So notice this is where I now have the conditional probability right here. So it's times the probability that the second card is a diamond given that the first one is a diamond. And all we have to do is just look at our tree diagram. Well, the probability that the first card is a diamond, that was at 9 out of 41. And the probability that the second card is a diamond, given that the first card is a diamond, and you might question, why do we really need to say that? Why can't I just say the probability that the second card is a diamond? Well, if you look at our tree diagram, that happened in two places. There's the second card's a diamond, and there's the second card is a diamond. Which one do I want? I want this one. How do I distinguish between this second diamond and this second diamond? I got to look to see what happened before that. Here is given the first card was a diamond. Here is given the first card was not a diamond. So that's why I must use the conditional probability here. All right, so let me backtrack all that. So the probability that the second card is a diamond given the first card is a diamond is nothing more than that 8 out of 40, which again is where we're going to get our 0.0439. So it's just another way of looking at it if you didn't have all the probabilities multiplied out in the end. The last part of first example says find the probability that he gets exactly one diamond out of two cards. All right, so let's look at this. One diamond gets exactly one diamond out of two cards. Well, there are four different possibilities of getting two cards. Well, this is where he got two diamonds, which is not exactly one. So we ignore that possibility. Here he got a diamond and not a diamond. Well, that is exactly one diamond, so we want to keep that. Here he got not a diamond, But then the second card was a diamond, which again is exactly 1 diamond. And then down here he got 0 diamonds, which is not exactly 1 diamond, so we don't want that. So what do we do with these probabilities now? Well, here's the thing. To get exactly 1 diamond means, get a little bit smaller lead here, exactly 1 diamond means that it either came, the diamond was the first card, or the diamond was the second card. What's the probability that the diamond was the first card? Well, that was that number, 0.1756. Or in our probability means to add, and these are disjoint events, there's no overlap between these two things. The diamond was the second card, well that happened with that probability, so therefore we add together our 0.1756 plus itself, or really we're multiplying by 2, which is going to give me 35.12%. So now let's look at a table here. So we're going to talk about joint versus conditional probabilities, if there is a difference there. And we're going to calculate some probabilities based on a table. So we're talking about marital status versus age of women again. This is an example we've used previously. So the probability that we get a married person. Well, here's married. And we're not talking about any specific age range here. So we're talking about all of our married people, which is our 58,929 out of 99,585, which happens to be 59.2% rounded. Now, is this a joint or a conditional probability? Well, conditional means we know extra information here, and they didn't give us any extra information. If it's conditional, then we would see the line with some other information written after it, but we don't see that here. A joint probability is when we have more than one thing happening, and we don't have more than one thing happening. We just have married as one singular event. So really in this one, this is neither joint nor conditional. This is just a basic probability. Number 2, we're looking for the probability of a person being married given, there's that line there, that they're 18 to 24 years old. Okay? Now, whatever that given information is, that means you only need to focus on that part of your table. So that means we only focus on these individuals here that are 18 to 24. And that means we ignore everything else. Forget about all these other numbers in here. They are going to play no purpose and no influence on our answer. So what's the probability that we find a married person? Well, there's that many married people out of this many 18 to 24 year olds. So that gives me about 24.1%. Now, since we have that particular symbol for the given, this is a conditional probability. We were saying, hey, we know some extra information about our married people, that they can only be 18 to 24 years old. All right, number 3, probability that they are married and 18 to 24. Well, now, let's erase all this. So they're married and 18 to 24. Well, here's married, here's 18 to 24. So we're specifically talking about these 3,046 people. Out of how many, though? Well, we didn't give any conditions here. There is no that symbol being used here. So we get to consider that it's this many people out of our grand total 99,585, which gives us, that's only about 3.1%. Now, what type of probability is this? This is a joint probability because we're combining two events here. Number 4, what's the probability that we get an 18 to 24 year old given that they have never been married? Now again, we have a conditional probability here. This is saying we only look at the never married people. So that means we only want to look at this row in our entire table, which means everything else we black out. We say, you know what, forget about this. We don't care about all the rest of these people. So now, what's the probability that we get an 18 to 24-year-old? Well, that's these 9,289 people. Out of altogether, in that age group, 19,309, which is about 48.1%. So that is a conditional probability there. And number 5, we need to find the probability of never married and they're 65 and older. Now, this is not a conditional probability. They did not give us extra information to consider here. So we are really doing a joint probability. Just do that. There we go. We're doing a joint probability because we're finding two things happening jointly. So never married and 65 and older, where do they come together at? On our table, that would be these people, 768 people out of, now we got to look at our grand total, 99,585, which is under a percent, 0.77%. And number 6, are events A and B independent? Okay, now A is, I don't know, what is A? I don't think I defined it. Okay, here is event A, that they're 65 and older, and event B is the event that they are widowed. So we want to find out, are these two events independent of each other? Does being 65 and older have any influence on someone being widowed? Does someone being widowed have any influence on whether they're 65 and older? So that's what we're going to find out. And there's two ways to do that. Number 1, is the probability of both events happening equal to their individual probabilities multiplied together? Well, let's look. So here I'm taking that, then I'm interpreting what A really means. A means they're 65 and older. B means that they are widowed. I'm just going to say W there. Is that equal to their product of their individual probabilities? Well, 65 and widowed, that's that number out of our total, 99.5 out of 585. 65 and older, that's those people. And widowed would be those people. So notice all three of those numbers are out of the same 99,585 grand total. So I just need to check, is this number, 8636 out of 95,585, equal to really these two fractions multiplied together? So let's see. This is really, that's really 8.7%. And if I multiply these two things together and convert it to a percent or a decimal, I get 2.04%. So those two things are not equal. And if they're not equal, that means they are not independent. They are dependent on each other. Okay? Now another way we could check for independence is just this. Is the probability of event B the same as B given A? So is the probability of being a widow the same as the probability of being a widow given that you're 65 years old or older? This way you only have to check two probabilities, and you really don't have to do any math, just checking. So the probability that you're a widow would be that 11,080 out of 99,585, and the probability of being a widow given you're 65 and older, well, that's these people out of, because said we're doing a conditional probability, we're only looking at this part of the table. So that's why we're taking this number out of this number and not the 99,585. So now we want to check, are these two things really equivalent to each other? And if I break them down into decimals or percents, I find out no, they're not really the same number. And since they're not equal, they're not independent. So there is a dependency on widows and being 65 and older. Okay, there is a relationship between those two events. And if you think about it, when are you typically going to be a widow? Okay, that means your husband or wife has died. And when are you typically going to have a spouse that dies? Well, when you're old, right? So doesn't it make sense that 65 and older and being a widow, that those two things would probably go hand in hand with each other, right? That they're going to be dependent upon each other? Now, we could look at maybe the younger ages and being widowed, and we could see if they're really independent or not. And we might find the same thing, and it might be a very small difference, but still, they would probably be not independent. But that's one way you can check to see whether two events are independent or not. So that is the end of the last video of chapter 5. So we'll discuss this tomorrow in class and do some more examples.